Hello and welcome back to Automata Grammars and Computability. In this video, we will start talking about Turing machines in earnest. Hopefully, you have already read the chapter in CIPSR. So section 3.1 is very helpful to understanding the basics, and then you get a little bit more in depth with 3.2, and that will help you understand this video. Previously, we've talked about the Chomsky hierarchy, and there are two classes of languages that I want to point out here, one of which is context sensitive, and the other one which is recursively enumerable. Now, we've already talked about context-free languages, and I want to point out that context-free languages and recursively enumerable languages overshadow context-sensitive languages in terms of like how often you're going to see these things in computer science. Now, because of that, we're going to go ahead and skip context-sensitive languages, and we'll go ahead and talk about recursively enumerable languages, which means that we'll be talking about Turing machines. So, just to remind us, we are in the part of the Chomsky hierarchy that talks about recursively enumerable languages, which is at the very top here, and those go along with Turing machines. All right, so we finally basically made it to the most powerful machines that we are going to be able to see. And it turns out that weird stuff happens when you allow all this level of computing. So just to give you a little history lesson, the person that created Turing machines, well, he didn't call them that, is the most general model of a computing machine. And he figured out that using these machines, there are problems that could not be what's called decided using a general method. Now, Alonzo Church also basically solved this problem, but he did it in a different way with something called the lambda calculus. And so Turing went to go work with Alonzo Church to obtain his PhD. And this is the basis for all modern computing, basically. All right, so these, like Alonzo Church and Alan Turing, were not computer scientists in a real sense because computer science did not exist yet. Another thing to point out, we've been talking about Chomsky quite a bit. So Noam Chomsky is also not a computer scientist. He is in linguistics, and he literally teaches foreign languages like French and German at MIT. So it's kind of interesting to see how the people that are at the forefront of modern computer science theory, these people are not themselves computer scientists. And of course, I'd like to point out another person that we've talked about quite a bit, which is that's Stephen Kleene of the Kleene star. And so he's made significant contributions to computability and decidability, which is what this whole class is about. Interestingly, another thing that he was into was being in the outdoors, and he discovered a variety of butterfly, which is named after him. All right, so going back to the main topic for today, which is recursively enumerable languages / Turing machines. A language is recursively enumerable, which is also called a Turing complete language or a Turing language, if there exists some sort of Turing machine that recognizes it. Okay, the word recognize is pretty important here. Now, what is a Turing machine? You can think of it as a DFA that has a tape, and that tape is unbounded. So over here, I have this image of the IBM 2420 magnetic tape drive. So there's literally a magnetic tape that's spinning, and this is a computer. Now, of course, that tape has some bounded length because it is a physical magnetic tape, but Turing machines theoretically are unbounded. Now, the stack of the PDA, the pushdown automata, those were also unbounded, but you always had to write to the top of the stack. So push or pop only at the top of the stack. The Turing machine has the ability to take that that header that and move it to any cell on the tape. Read the symbol there and even write or replace the symbol there. So, like I said, that tape can be thought of as being an unbounded array of symbols. And we've seen before the input alphabet sigma. And now we have a tape alphabet gamma. So the pushdown automata had a stack alphabet. Here we have a tape alphabet. It's pretty similar. The input string is the thing that's on the tape when the Turing machine starts. All of the other tape cells are usually are blank, which is usually denoted with like an underscore sort of symbol. Now, there are lots of ways to conceptualize Turing machines, and maybe one physical way to do that is with what's called the poor mug in a box. So here's literally this person who is going along these tracks, and the tracks will stop on a cell. And so as he's going along, it's a two-way unbounded read-write tape. And the actions are basically, what state am I in? And then read some value, read a 0, for instance. And he knows the rule. If I in state Q and I read a 0, I must write a 1 and move right. More mathematically, we have the model of just like a finite, it looks like a finite automaton, but of course what you can write on the head on the tape has changed here. So looking at the arrows between the states, I have an input symbol. I have the ability to write the symbol, so it's separated by a slash, and then move left or right. So that's L or R. Let's look at this example a little bit more. And what we see here is instead of writing it as a or drawing it as what looks like a finite automata, except the arrows say something specific, I could also write it as a table. So this table has, for example, current state A. This symbol that I'm reading is 0. I'm going to print the symbol 1. I'm going to move the tape right, and then it will tell me what the next state is. And you can, instead of having a table, you could also write it as a sequence of tuples. So I've shown you the Turing machine as a drawing. I've shown you the Turing machine in table form, and I've shown you the 5 tuples. We have not quite yet specified what all is on the Turing machine. So as usual, we need to define everything for the Turing machine. Here I have the states Q, the input alphabet sigma, the tape alphabet gamma, the transition function delta, the start state Q0, the set of accepting states, and the set of rejecting states. It's important that the accepting states are not equal to the rejecting states. And it is also important that we have the blank symbol, which is part of the tape alphabet, but it is not part of the input alphabet, and that the input alphabet is a subset of the tape alphabet. The definitions are going to vary slightly. So I guess this is Hopcroft or Ullman. I don't actually know. But this guy here. So looking at this picture, looking at this definition, you can write a 1-tape Turing machine as a 7-tuple. I've already talked about Q and gamma as the states and the tape alphabet symbols. Here they're using the letter B for the blank symbol. Sigma is gamma without B. You have an initial state. You have the set of accepting states. And the initial tape contents is set to be accepted by M if it eventually halts in a state from F. Delta here is a partial function. Q without F cross gamma to Q cross gamma cross L and R. L is left shift, R is right shift. Delta may not be defined on the current state and the current tape symbol, which would mean that the machine would halt. So here it's used the letter B instead of the underscore symbol. We have the set of finite states, which is now denoted as capital F, which we've seen before. And then we have this delta, which is defined in this particular way to be a partial function. So the next thing that we want to talk about now that we have the definition of Turing machines is how to think of it as kind of programming, because that's what you're doing with actually when you program. You think about all the substeps that you need, maybe subroutines, and then you think about how to put them together. So just like we did with Thomson's construction, you can stitch together a program using existing Turing machine programs, right? And this is actually how, if you're writing something in more high level code, Java, C, Rust, assembly, whatever, you're basically thinking about what are those small things that I need and how do I put them together. This is the basis of all we do in programming. A note here is that the other automata, which include DFAs, NFAs, deterministic pushdown automata, and let's see if I can put my video somewhere. Won't bother. The text pushdown automata. So these other automata are always going to halt. So I've kind of mentioned this already. I said, if we end up in this kind of state, it will halt. But the way that it works with other automata is it's going to process that input string. And we've always been reading it left to right. So far, we could never go back. And you end up in a final or accept state. It always halts. This kind of yes or no problem is called a decision problem. It decides accept or reject. Now, that means, okay, if the input string is in the language, the machine accepts. Otherwise, it rejects. Because these automata always halt, eventually, might take a while, they reject input strings that are not in their language. So they always accept or reject. But this is not true for Turing machines. So Turing machines have this concept of recognizability and decidability. Now, we just mentioned that all the other automata do either accept or reject, which means they decide problems. Now, if a specific Turing machine halts, accepts, or rejects, then that Turing machine decides its language. But there is this concept of Turing recognizable languages that are not decidable. So, recognizability is basically this possibility to have this third thing happen: accept, reject, or loop forever. So a specific Turing machine may or may not halt. Turing machines for Turing decidable languages will halt on every possible input, right? So that's what it means to be decidable. But a language just needs to be recognized to be recursively enumerable. A language is recursively enumerable if there exists a Turing machine that recognizes that language. Such a Turing machine must accept, meaning it halts in an accept state for every string in the language, but it says nothing about what happens if that string is not in the language. Here, I'm going to just give you a chance to, you can pause the video and try this example out. Let's say that you want to draw a Turing machine. Let's assume that that Turing machine starts in state Q0 on the leftmost input symbol. And now we're going to write a couple of Turing machine programs for a couple of small problems. So move to the first empty tape cell after the input. 2, move to the last symbol of the input. 3, the input is a number n in unary notation using the symbol x. The Turing machine should accept with n plus 1 left on the tape. And 4, the input is a number n in binary. The Turing machine should accept with n plus 1 left on the tape. All right, so you can keep watching the video or always go back here and attempt these problems. So let's go ahead and talk about what it would look like to move to the first empty tape cell. Let's assume that our alphabet is 0, 1. The machine starts at the first symbol of the input, which is by definition. So we see here, and this is just going to accept. It's just going to read 0, write 0, so it doesn't do anything, and then it keeps just going to the right. It just keeps reading. Read 1, write 1, go to the right. And I could have probably drawn this on the same arrow. And then here I have this blank. So since the input will end with a blank, when I see a blank, I can just write a blank, I can go to the right, and then I'm in the tape cell that is, I'm in the first empty tape cell, basically. Good. So this is just reading left to right. But there's a problem. So let's, if you didn't catch it, hopefully this fixes the problem, which is if I read and I go to the right, because I always end up having to move, I'm going to be one past the last cell. And so I need to be able to move back to the left. So here, this state 1, 0, 0, 1, 1, it just keeps moving to the right. If I see a blank, write a blank, go to the left. And then this still hasn't covered everything, which is what if the tape starts out blank? So if the tape starts out blank, then we are going to go ahead and reject. So in the Turing machine simulator, the Turing machine halts and rejects whenever there is no transition it can take. So in our diagrams, this is also the case, but it's good to explicitly label the reject states. Great. So hopefully you can walk through that example. I recommend trying it yourself and coming up with questions that you have about what was happening with those different drawings. Now let's talk about the unary incrementer. So because I only have one letter in my alphabet, which is X. So think of this as like a tally language. Like I'm just going to keep marking to see how many days have passed. And so in this solution, right, as long as I see X, I'm going to just write X and I keep writing. And the second I see a blank, I'm going to write an X there and then move to the right. So good. I'm all I have to do is go to the end and write one more tally mark, which makes sense as a program to write. All right. So I'm actually going to stop here. I know I gave you more examples of Turing machines than ones that I actually went over in this video, but I don't want the video to be too long. So please go through that example that I did more slowly. The video is pretty quick. Go through the unary example a little bit more slowly. And from there, you will be able to start drawing Turing machines for some of the other problems that I provided as well.